Okay, hello everyone. I'm Mike Galvin. I'm a spacecraft design engineer at Princeton University. I work as the lead mechanical engineer for a few different NASA flight projects, and I'm also the principal investigator for our undergraduate CubeSat program or nanosatellite program, which you can check out at tigersats.princeton.edu. I'll be talking about the merit of a variety of different acceleration measurements that you can make during launch and orbit, as may be applicable to some upcoming max IQ opportunities or missions or your suborbital mission payloads, all different opportunities where you may want to measure acceleration with some kind of accelerometer during launch or in orbit, or even, I forgot to mention here, during reentry, which would be especially interesting for our suborbital program. So the first thing I want to highlight is a schematic like this from the Falcon 9 user's guide. It shows kind of a cartoon of the typical launch profile of a Falcon 9. And we mostly think about rocket launches as vertical. When you see video of the rocket launches on YouTube or anywhere, you see the rocket lift off and mostly go vertical. But the dominant component of a rocket's trajectory is really horizontal. So like parallel to the Earth's surface in order to accelerate it to orbital speed. So it takes off vertical, but it quickly starts turning horizontal to get up to orbital speed. And the way that looks is you'll have a lot of acceleration in the axial direction for sure. But you know that a change of direction is also a type of acceleration. So your payloads that are in the nose cone of the rocket, in addition to seeing axial accelerations, are also going to see a variety of lateral accelerations during the launch. So this is an example of how you might see something like that defined. This is also pulled out of the Falcon 9 user's guides. I've mentioned a few times in the program that it's really funny that the major rockets of the world actually literally have public user's guides. They're like user's manuals. You can all download them, and you can read into how the rocket works and what type of environment the rocket provides, and how you need to be able to interface with the rocket, how you mount to it mechanically, how you interface with it electronically. It's all right there in the manual. And some of the interesting part of the manuals are the environments that each different rocket subjects the payloads to, because each rocket provides its own unique environment. But this is one of the most important graphs that's in every rocket user's guide. It's called the limit loads, or often called the quasi-static loads. And it's just the plot of a variety of G loads that you can see in different directionality. So axially in the positive direction, in the minus direction, and then lateral G loads also, which all that refers back to the launch profile that I was showing you. And it's probably important to note that there really aren't any real static loads during a launch. The launch is a very vibratory environment. It's very dynamic, and everything's shaking and chattering. So there aren't really any boring static loads during a launch. But there are some semi-steady load factors resultant from that axial ascent and lateral turn that the rocket does. And certainly there are some load factors that you can assume that most of the dynamic vibrational G loads fall under or are enveloped by. And that's what this plot will define. So on this plot, you're going to see a payload, a typical payload in the nose cone of a Falcon 9 rocket is going to see +6 Gs in the axial direction, or maybe down to -2 Gs in the axial direction. And that corresponds, of course, to liftoff, very high axial loads during liftoff, during the max Q part of the launch, which is the maximum dynamic pressure that the rocket is subjected to during launch when it's really, really fighting air drag. But then you see some negative axial accelerations here also, and that's the sort of thing that can happen when during the launch the engines cut off or a stage separates, and the upper stage might decelerate rather than accelerate momentarily, and you may see these negative axial loads, G loads, in those scenarios. And then those lateral loads you may see just due to the pretty random vibratory environment going on in the nose cone, but also just due to that turn towards a horizontal trajectory that I showed you on this sort of cartoon ascent diagram. So we're really interested in what loads our payloads might see on the Blue Shift rockets and on other rockets that the MaxIQ payloads might end up on. And what's interesting about the Blue Shift program is that they're still writing their user's guide now, and they don't have a lot of these environments defined yet or even measured themselves yet. So the MaxIQ program is an interesting opportunity for us to take these kinds of measurements during launch and to help them write their user's guide and define their environments, because everybody getting up and running in this workflow is all, we're all just going to help Blue Shift get to orbit faster, and that's what we want. We want to help them with their suborbital program, and we want to help them develop as an orbital launch service provider as well. And so we can really do some interesting work here in defining some of these G loads that our payloads are subjected to in the Blue Shift launch environment. So you can see here the range of G loads that we're going to be interested in are +6 to -2 Gs in the axial direction, or ±2 Gs in the lateral direction. And then you can see a variety of different combinations of those. So here's some launch case where the payload sees 3.5 Gs actually simultaneously with 2 Gs laterally. And so that's why you get these sort of interesting shapes, which defines all possible G load permutations. And then, of course, like I said, the loads during launch are not really static. They're very dynamic. They're very vibrational. And the true launch environment that you'll see defined in each of the rocket users guides is a random vibration environment. The users guides will also define a sinusoidal vibration environment, but there isn't really true sinusoidal vibration going on during launch either. The sinusoidal environment is usually a good way to check the workmanship of your payload. If you just shake it back and forth sinusoidally very fast and very hard, you can check if any screws come loose or any of your glue comes loose or anything like that. The sinusoidal vibration environment defined in the user's guides is not usually really a great representation of the launch environment. During the launch, your payload is vibrating very randomly. But even a random vibration environment can be defined quantitatively and enveloped and characterized and analyzed. And so you'll usually see the random vibration environment defined in the user's guide as a vibration spectrum. So in the Falcon user's guide, you can see here that there are components of random vibration with frequencies all the way from, looks like 20 hertz all the way to 2000 hertz. And what that means is all of those frequencies are present in the vibration almost at any given time of the launch. You're getting fractions of those frequencies in the vibratory excitation of your payload, but at different levels for each constituent frequency. And that's how you end up with this vibration spectrum, a random vibration spectrum. And so the way that you figure out what that spectrum is you can do a Fourier transform. So you'll have some transient signal, some transient function representing the vibratory motion of your payload or of your sensor. Your sensor is going to be sensing its vibratory motion or its vibratory acceleration or its vibratory velocity. You can integrate or derive all these values to get back and forth from each of them. But when you have this very random transient signal defining the vibratory motion of your payload, you can apply a Fourier transform to that signal, and it will tell you the constituent frequencies in that signal and the relative weight, so the relative fraction really of each of those frequencies and the relative strength of each of those frequencies in the overall random vibration spectrum that the payload is subjected to during launch. And this math is actually over my head these days as well. I'm just a simple engineer. But I've included some links here if you want to learn more about Fourier transform and dig under the hood into how that's done and how to calculate it from scratch if you'd like. So the next environment that you might be interested in measuring with an accelerometer is a shock environment. And a shock environment is basically just a very fast transient vibration environment that decays very quickly. So it's not a sustained vibration. It's a short transient vibration, but it can be very strong. It can be a very violent vibration for a very short amount of time. And I bring the Falcon 9 launch schematic back up to show a few of the moments of launch that are defined. Here you can see here a few moments during launch are defined as high shock moments when your payload may be subjected to high shock loads. So that's just basically the first moment of takeoff when some clamps that hold the rocket down are released. You may get high shock loads at stage separation when the first stage separates from the upper stage. You might get high shock loads again when the fairing or the nose cone pops open. A lot of these separations and fairing separations are performed explosively using ordnance, or you might think about it like gunpowder. A lot of these operations are still performed explosively, and so you can get pretty high shock loads. And then there's just a lot of energy stored in clamping the stages together or clamping the nose cone halves together, and all that energy gets released instantaneously when you separate the stage or you pop off the nose cone. And so those are high shock events, and that shock can travel all the way through the nose cone or all the way through the upper stage up to your payload in the nose cone. And then one more typical high shock environment is payload separation. When the spacecraft, the final payload, is popped off the top of the upper stage. And this is often, although it's changing these days, but it's often performed explosively as well with explosive hold down or release devices. So again, it can impart pretty high shock loads on your payload. So yeah, one of the most characteristic shock loads again is happens at spacecraft separation. And what you're seeing here is the payload or the spacecraft, the primary payload of the launch, which is the spacecraft stored in the nose cone, is usually held on to the nose cone or to the upper stage, held in the nose cone by what's called a clamp band. And a clamp band, it really is like just a metal belt. And it's a belt that you tighten like you would the belt on your pants. You tighten it really tight, and then this belt holds the spacecraft really tightly within the nose cone atop the upper stage of the rocket. So that's what you're seeing here. You're seeing these guys in their clean room suits, either fitting the spacecraft onto the clamp band, or maybe they're checking the fit of the spacecraft in the clamp band. But that gold thing you're seeing there is like the belt that's holding the spacecraft on there. And it's held on very tightly. It's storing a lot of energy to make sure that the spacecraft doesn't tip off the upper stage, doesn't pop off, doesn't free itself prematurely. And so oftentimes the belt has to itself be released explosively as well, using some type of ordnance, or sometimes it's more like a bullet with an anvil and vice mechanism that severs a band that's holding the clamp band together. But there's a variety of high shock release mechanisms involved in these clamp bands. And these days there's some low shock release mechanisms as well. But again, on a typical launch, this is often a high shock event, releasing this clamp band and releasing the spacecraft into a free flying orbit. So again, in the user's guide, you'll often see the shock environment defined. This is the Falcon shock environment. They give one environment that basically envelopes, or it covers all those different shock events. If you can qualify your payload to this shock environment, then your payload should be able to survive all possible shock events during a Falcon 9 launch. And again, you can see that it's a vibration spectrum. It's a shock spectrum, not a single frequency. It's a magnitude in G's defined at each frequency. And this really defines a curve, but they're showing you some discrete points in the curve. But it defines a magnitude of shock across a range of frequencies that are constituent in the shock excitation imparted on your payload at the high shock events. And again, these are all unknowns for the Blue Shift launch environment. So these are all interesting things that we hopefully will have the opportunity to help them measure. And these are all acceleration values. So they're all most appropriately measured with accelerometers. And then once you're on orbit, you've finished launch and you finished launch and your payload has separated from the upper stage of the rocket, the clamp band has released, and you've been released into a true free flying orbit. You're still not done with acceleration measurements because your spacecraft, unless actively controlled, it will be tumbling slowly or quickly, and it will be subject to disturbance torques in the orbital environment, very gentle disturbance torques that are imparted on your spacecraft, for instance, from solar pressure, just differential pressure from the sun, from photons hitting faces of your spacecraft, or from a gravity gradient, or even for some residual drag up there, up in the low Earth orbit. You think that there's no air molecules up there, but there may be, depending on your altitude, some trace residual air molecules up there that are imparting drag on your spacecraft, and that can manifest as a very gentle disturbance torque on your tumbling spacecraft. And then maybe you have an advanced spacecraft and you're actually controlling the orientation and pointing of your spacecraft. And you can do that a variety of ways. I'm showing here torque rods, magnetic torque rods that are typically used on small CubeSats. These are just electromagnets that are activated or deactivated in some intentional sequence to interact with Earth's magnetic field in a low Earth orbit altitude range to basically to self-impart torques on your spacecraft and to control your own pointing, to steer your spacecraft. So spacecraft, whether they're actively controlled or whether they're passively tumbling, you usually want to have some knowledge of your orientation, and you will attain knowledge of your orientation via an attitude determination system. I'm showing in the top right here an advanced component of an attitude determination system is a star tracker, which is basically a very advanced camera that's going to it's going to detect a bunch of stars in a field of stars that it's pointed at, and it will be able to back out or reverse solve for what part of the night sky that it's looking at. And in doing so, you'll be able to back out in what direction your spacecraft is pointed. So very advanced spacecraft have star trackers that help them know their orientation. Similarly to the torque rods I'm showing here, your simple spacecraft may have a magnetometer on it, which is similar to a torque rod, but instead it's a passive device where you're actually taking measurements of the ambient magnetic field, and that can help you determine your orientation in low Earth orbit. But all of these things are used in combination, usually with a filter, often a Kalman filter, because you get all this different telemetry from the star tracker and from the magnetometers, and you want to combine it all to figure out the most accurate pointing orientation that you can, and where are you pointing, and how fast are you rotating, and how fast is your rotation accelerating. So angular acceleration, angular velocity, and this is all usually solved for on a spacecraft as part of a Kalman filter of all of these different sensory inputs. And this brings us back to accelerometers, because an accelerometer, or in the case of angular velocity or angular rotation, angular acceleration, instead of a linear accelerometer, you're going to be using a gyroscope, an onboard gyroscope, to sense your angular velocity or your angular acceleration. And those are also sensory readouts that go into your Kalman filter, because you can integrate your angular acceleration or your angular velocity to yield what is your angular slew, how much have you turned, what direction are you pointing now, and all of those all those gyroscope inputs can be combined in your Kalman filter to really help you know exactly what your orientation is and your roll rate and things like that. And then maybe our CubeSats have some type of propulsion of their own. And so I'm showing here like a simple CubeSat thruster. I don't know what type of thruster this is, but this is probably just some rudimentary CubeSat thruster. But in order to know how your thruster is performing, how you're accelerating, in order to integrate possibly how much you've accelerated, what your before and after velocity is, before and after a thrust or burn. You're again really going to want to rely on the telemetry readout from your onboard linear accelerometers. And from that, you should be able to integrate or do some math and figure out how much you've sped up and maybe what your before and after speed were and how fast you're going now. So still keeping with linear acceleration, in particular for our suborbital payloads, but also even in orbital payloads, when you re-enter the atmosphere, you start hitting air drag again. And this is what's responsible for eventually, hopefully, burning up your nanosatellite, not for our suborbital payloads, but for orbital payloads. Most orbital payloads, you want them to burn up before they fully re-enter the atmosphere and maybe fall down on somebody. So when you're at the end of your satellite's life, a lot of times you're coming back down through Earth's atmosphere and burning up and encountering strong air drag and strong deceleration. And if your satellite hasn't burnt up yet and it's still alive, you can measure this linear deceleration. And from that, you can back out what type of air drag you may be encountering. And interestingly, we learned in a prior program that there's a regime of ultra low Earth altitude, extremely low Earth altitude, where the air density from day to day or from month to month is not very well known. And one of the ways that NASA tries to figure out this air density is from very gentle decelerations, measuring very precise decelerations as a spacecraft re-enters through that altitude regime. And so this is just another interesting accelerometer measurement that you can take with your nanosatellite. And perhaps unique to our suborbital program, even after reentry, there's going to be some interesting decelerations, potentially violent decelerations that we may want to understand and help Blue Shift understand the magnitude of, or perhaps just how violent some of these decelerations are, so that they can publish it in their users' manuals. And so one that I notice here is parachutes. When our suborbital stage is bringing all of our payloads, so our payloads aren't going to be ejected from the upper stage of the suborbital rocket. They are going to remain protected comfortably within the nose cone of the rocket, and they're going to come back down through Earth's atmosphere within the nose cone. But after reentry, Blue Shift's parachute is going to deploy, and maybe that will be a pretty high shock moment of the descent. And then for sure, the parachutes will slow things down considerably, but certainly once we reach back down on the ground and crash, hopefully gently, into the ground or into the ocean, that will be probably another high shock event during the mission. And it will be interesting for us to characterize what the deceleration or shock loads on our payloads are at these moments of suborbital descent. So just in practice, what this all means is choosing accelerometers for your mission, or configuring your accelerometers or gyroscopes for your mission appropriate to the expected environments. And so I'm showing here one of our favorite inertial measurement units from Adafruit. This is the BNO 055. This is a pretty advanced inertial measurement unit, which includes not only linear accelerometers, but gyroscopes for angular acceleration and velocity measurements, and magnetometers for ambient magnetic field measurements. But primarily, we're talking now about the accelerations, linear and angular. So we're talking about the linear accelerometers and the gyroscopes on this inertial measurement unit. And we want to use this BNO 055 accelerometers on our payload, on our Blue Shift Max IQ payload. But we need to be sure that when we read the 100-page data sheet for this these accelerometers, you can see that you can actually do user configuration of the accelerometers to make sure that they're measuring the right range that you're expecting to be subjected to during launch or during orbit or during descent. So you can set for this accelerometer, you can set to measure within plus or minus 2 Gs, plus or minus 4 Gs, or plus or minus 8 Gs, plus or minus 16 Gs, and you set that up with your own code at the initialization of the inertial measurement unit. And you know, again, we don't really know what the acceleration environment, the G load environment, or the shock environment is going to be for the Blue Shift missions, but we just use a rule of thumb from the Falcon 9 payload and tried to measure up to plus or minus 8 Gs, knowing that we would capture the quasi-static loads of a Falcon 9 payload if we correctly set our measurable range to that level on our BNO 055. The trade-off here is the smaller range that you use, the more precision that you get within that range. And so if you go all the way up to the plus or minus 16 Gs, then you just get less precision. And you know, maybe that's important for when you're trying to measure those very gentle decelerations during orbit or during reentry. So there's a lot of other, again, using the Adafruit BNO 055, there's a lot of other user configurable options that you set up in code during the initialization of the accelerometer and the IMU and the gyroscope and the magnetometers. And the application here, the practical application of what we're talking about here is making sure that you preset your measurable ranges in your accelerometers to ranges appropriate to your mission. And so the bandwidth of your accelerometer, that's more important for transient acceleration measurements, so measuring vibration. You can set the range rate of degrees per second that your gyroscope is going to be measuring angular velocity in. You can see the achievable measurable shock range of this BNO 055. And there's all sorts of other user configurable options under the hood of this accelerometer, this inertial measurement unit. And this one's important down here. These are output data rates. So you can see this is how fast you can read out each sensor on the BNO 055. So you can read out the linear accelerometer and the angular gyroscopes at 100 hertz. So you can read them out 100 times per second. And it's up to you to figure out, is that fast enough to measure the vibration spectrum? For instance, if you're trying to do transient vibration characterization or transient shock characterization, is 100 hertz going to be fast enough readout to fully characterize the environments that I'm being subjected to? Or am I going to be missing some key readout frequencies key excitation frequencies. So these are all just things to think about when you're setting up your nanosatellite accelerometers. And I think that's it. I hope that was enriching, and good luck with your Max IQ payload experiments and setups and everything. Hope everyone's having a great time.